Hello friends, today we are going to study aryl halides. In the 6th lecture of organic chemistry, we have planned to study different reactions of aryl halides. In reactions of aryl halides, we have taken chlorobenzene. In this lecture, we are going to study first reaction nitration, second reaction sulfonation, Friedel-Crafts alkylation, aromatic nucleophilic substitution reaction, SN2AR aromatic nucleophilic substitution, Benzyne mechanism, reactivity and relative strength of carbon halogen bond in alkyl, allyl, benzyl, vinyl and aryl halides. So friends, we will start to the reactions of chlorobenzene. Aryl halides shows aromatic electrophilic and nucleophilic substitution reaction at aromatic nucleus. The first reaction of chlorobenzene is halogenation. Chlorobenzene, when reacted with chlorine in presence of ferric chloride FeCl3 to give orthodichlorobenzene and paradichlorobenzene. Consider this is the reaction. This is a chlorobenzene. Chlorobenzene when reacted with Cl2 in presence of Lewis acid catalyzed FeCl3, it gives orthodichlorobenzene and paradichlorobenzene. Next reaction is nitration reaction. In nitration reaction, chlorobenzene when heated with nitric acid, it gives 2-chloronitrobenzene and 4-chloronitrobenzene. So this is a chlorobenzene when it is reacted with mixture of concentrated HNO3 and H2SO4, and when this mixture is heated to certain temperature, it gives 2-chloronitrobenzene and 4-chloronitrobenzene. Next reaction is sulfonation reaction. In sulfonation reaction, chlorobenzene is allowed to react with sulfuric acid to give 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid. Consider this reaction. This is a chlorobenzene when it is treated with concentrated H2SO4 and this mixture is heated to certain temperature. It gives 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid. Next reaction is Friedel-Crafts alkylation. In this reaction, chlorobenzene reacts with methyl chloride as a alkyl halide in presence of Lewis acid catalyst such as aluminum trichloride to give para-chlorotoluene. Consider this is this reaction. In this reaction, chlorobenzene is reacted with any alkyl halide such as methyl chloride, ethyl chloride in presence of AlCl3 aluminum trichloride. It gives para-methyl chlorobenzene or para-chlorotoluene. Next reaction is aromatic nucleophilic substitution reaction, replacement by OH group and effect of nitro substituent. Unsubstituted benzene is treated with a nucleophile. The attack of nucleophile is much more difficult due to two reasons: a repulsion of pi electron cloud to nucleophile and inability of accommodation of extra electrons of nucleus in delocalization. So friends, this is the aromatic nucleus and this nucleophile having a negative charge electron cloud, and in benzene ring also there is an electron cloud, and on nucleophile again there is an electron cloud. Electron repulsion occur, therefore there is too much repulsion in nucleophile and pi electron cloud. Therefore aromatic nucleophilic substitution reactions are reluctant. It is less extensively observed, and once nucleophile attack on aromatic nucleus forcefully. So this is the intermediate form in the reaction. Aromatic nucleophilic reactions are of different kind. So in our syllabus, we have to study SN2AR, aromatic nucleophilic substitution reaction bimolecular. Consider one reaction. Nitrobenzene on fusion with KOH in presence of air gives orthonitrophenol as a major product with little amount of para-nitrophenol. So this is the reaction. This is a nitrobenzene, and on nitrobenzene, this hydroxide ion, this nucleophile, try to attack on aromatic nucleus. It attacks to ortho position with respect to nitro group. This pi bond gets shifted towards the nitro group, and this double bond is get shifted on oxygen atom. So this attack of OH minus nucleophile occur very slowly. This is a slow step, and thus once OH minus attack on this ortho position, O oxygen atom acquires negative charge, but this is not a stable one. Again, this O minus get delocalized, and pi bond in between nitrogen and carbon, this is get reversed, and there is a loss of hydride and H minus ion, and finally we get a orthonitrophenol. So this intermediate is for this reaction, and this is the final product. This reaction having a two-step. First step is a slow step, and in this step there is a first step there is an attack of OH minus, and in the second step there is a loss of hydride ion. Rate of this reaction SN2AR is dependent on concentration of nitrobenzene and concentration of hydroxide ion. As in rate equation, there is presence of nitrobenzene as well as nucleophile. This is a bimolecular reaction. Thus, electron withdrawing substituent present in an aromatic nucleus, it directs electrophilic attack to the meta position, but in aromatic nucleophilic attack, it directs ortho and para positions. The most common aromatic nucleophilic displacement reactions involve the displacement of halogen atom from halide compound C6H5Cl, C6H5Br, C6H5I, activated by electrons withdrawing group. Friends, in aromatic nucleophilic substitution reaction, there is very important reaction mechanism known as a Benzyne mechanism. This Benzyne mechanism consists of use of potassium amide in liquor ammonia or sodium amide in liquor ammonia. This reaction consists of one or more nuclear hydrogen atom are substituted by the nucleophile is called as aromatic nucleophilic substitution reaction. So consider this is the reaction. This is chlorobenzene. NH2 minus nucleophile attacks in place of chlorine in liquor ammonia, and this reaction takes place at minus 33 degree Celsius. There is a substitution, nucleophilic substitution. When para-chloro-methyl benzene is treated with NaNH2 in liquid ammonia at minus 33 degrees Celsius gives not only the expected para-amino-methyl benzene but also the unexpected meta-amino-methyl benzene in large percentage. So this is the reaction. This is a para-chloro-methyl benzene. It is reacted with NH2 minus, this is a nucleophile. It is obtained from sodium amide, and solvent is taken as a liquor ammonia, and this reaction requires temperature minus 33 degrees Celsius. So friends, see the products. There is a replacement of chlorine by NH2 minus. This is the first product known as a para-amino methyl benzene. It obtained in 38%. And second product, interesting product is obtained. Chlorine is present to the para position with respect to methyl group, but this is the para position, but incoming nucleophile does not get substituted in place of chlorine. It is to the meta position. So this is a meta amino methyl benzene, and this product is major in quantity, and it has 62% yield. This mechanism is studied like this. First step consists of abstraction of protons, formation of arene. So friends, what happens here? This is a para-chloromethyl benzene, and this nucleophile abstracts the proton, and this bond gets shifted in between this carbon and this carbon, and when this bond is get shifted to this carbon, having a will be having a 5 bonds, therefore this chlorine is get eliminated, and this carbon, both carbon of aromatic nucleus having a 3 bonds, that is a alkyne type intermediate known as a benzyne intermediate. And once benzyne intermediate is formed, second step consists of attack of nucleophile, that is NH2 minus attack in different way. So this is a benzyne intermediate obtained in the first step, and NH2 minus nucleophile attacks in different way. The first way of attack is NH2 attack in place of chlorine. So here NH2 get attacked to the para position, and we get here para amino methyl benzene in 38%. And second probability, or which has a more extent, that is NH2 minus attacks to the meta position, and this bond is get shifted here. NH2 attack either here or either to the para position, and there is a formation of meta amino methyl benzene in large excess quantity. Benzyne react with furan and undergoes Diels-Alders reaction. So friends, the benzyne intermediate reaction has many applications. So this is the first application, reactions of furan with benzyne intermediate by Diels-Alders reaction, and we get a adduct, and we can synthesize different compounds. So see here, furan is there and benzyne is there. So these two diene and dienophile get attacks. So this is a diene and this is known as a dienophile, and attacks occur by Diels-Alders way, and there is a formation of this addition product, and on treatment with mineral acid H plus and methanol, we get a beta naphthalate. So this bond is broken, this bond is shifted here, aromatization occur, and this bond get baked, and this oxygen get converted into OH and known as a 1-naphthol. In the absence of second reactant, suppose we have not taken the furan, then this benzyne intermediate undergo dimerization, self-trapping, and this is known as a self-trapping very rapidly, and form stable biphenyl product. So we have not taken here furan. 1 mole of benzyne reacts with another mole of benzyne. Self-condensation takes place, self-trapping occur, and there is a formation of biphenylenes. These 2 rings having a 4-membered ring. So this structure is known as a biphenylene. Now, lastly, we are going to discuss reactivity and relative strength of carbon-halogen bond in alkyl, allyl, benzyl, vinyl, and aryl halides. For study, we have taken one table, and the table is given on the next slide. So this is the slide. This is the table. It shows reactivity of different halogen atom, chlorine, bromine, chlorine, bromine. So bond length is given here. Chlorine having a more bond length, chlorine having a less bond length as compared to bromine, and thus fluorine, chlorine, bromine, iodine. So iodine having a, again more bond length. We have taken just chlorine and bromine. As we go from fluorine to iodine, bond length of carbon halogen bond goes on increasing here. And again, uh, bond length also depends upon the alkyl group. Here we have taken methyl, here we have ethyl group. Bond length is same in CCl, but bond length in CBr is reduced by a certain value. In first compound there was a 1.99, but it is 1.91. So bond length depends upon which type of alkyl group is attached to halogen atom and which halogen is attached to the carbon atom. This also decides various functional groups also decides the bond length. So in table, detailed bond length is shown of different compound and dipole moment also get affected. See the dipole moment here. Chlorine RCl dipole moment is 2.05, but whenever bromine is there, dipole moment is less. We know fluorine is the most electronegative atom, therefore dipole moment goes on decreasing from fluorine to iodine, and thus chlorine having a less dipole moment, while chlorine having a more dipole moment, but bromine having a less. In this way, we can study dipole moment and bond length and reactivity. As we studied dipole moment decides the reactivity, bond length of different compounds. Here we have taken here first compound methyl group, ethyl group, propyl group, butyl group, tertiary butyl group, allyl group, and aryl group. In this way, whenever we have a various types of alkyl group attached to the halogen atom, at that time bond length tremendously changes and its dipole moment also changes. Reactivity, ultimately its reactivity is get affected. There is a variation in the reactivity. So friends, in this way we have finished this big topic, alkyl, aryl, halides. We have seen alkyl halides, preparation of alkyl halides, reactions of alkyl halides. Similarly, in the second section, we have seen aryl halides, what is meant by aryl halides, then preparation of aryl halides, nomenclature, reactions of aryl halides, etc. So, after discussing this, I think you have much idea regarding this topic. You can solve the problems or reactions based on this topic. Thank you very much.